some graceful delay in the schedule, but we are still mostly under control. We have a follow-up presentation from the side of the RIS5 activities within EPI. This will be done by our colleague Filippo Mantovani. Filippo has been active all these years and has been leading Stream 3 in the recent incarnation of the project. He has been instrumental for the development and continuous maintenance and improvement of the SDVs, and he has been doing his own performance studies and case studies using this platform. You saw yesterday for the people attending the private meeting that we have this ongoing development of the SDVs. SDVs have become available publicly as well, and Filippo and his team have been providing valuable support and I would say education to the teams that actually make use of this resource.
Portable microphone. I can use this. Yes, thank you. Thank you for the introduction. How long should it be? Okay, good. Thank you. Thank you for the invitation. And yes, like Manoli said, I'm here to share a little bit the experiences and the learning with the EPAC test chip. So let's move. I mean, there are a couple of things that I wanted to clarify quickly, and then there is one part that is more like a little bit of the insights that we have been gathering, studying complex scientific codes with this machine. And there are some things that are probably converging with what was strange convergence with what Jesus was presenting before. I promise I have less paraver traces, but I cannot promise that there are none. So I need a little bit of context. This probably you already heard 1,000 times, but so EPI project, European Processor Initiative, 2 lines of development, a CPU development called REA, an accelerator development called EPAC, okay? One is ARM, REA is ARM, the other one is RIS5. In the RIS5 accelerator, there are different contributions, so different accelerators, STX, VRP, so stencil operation, variable precision, and then VEC. VEC is the combination of a RISC-V scalar core working together with a vector unit. I think this is the shortest summary that I did in my life about EPI. One slide and good. We are saving time. Okay, good. So now I start going into details of this part. Okay, so this is just to put you in context. Good. So the core is called Avispado, at least in the first incarnation of the first tape out of EPAC. What's special? It boots Linux. Is a standard scalar in order RISC-V core, and it is connected to a VPU. So the two, say, technological things that in this block diagram that has been shared by Semidynamics, you have this block that is basically you are here in the memory queue. So the core is able to maintain in flight a lot of requests to the memory. Okay, that's one architectural thing that is really important. The other one is this one. Here you are in the vector queue. There is the OVI, Open Vector Interface. So this is basically a plug like the ISS where you can plug different spaceships, okay? So this is a plug in which that has been standardized. You can download it and you can, in principle, write your own vector unit, and you can plug it so that the core can work with your VPU. And here is where the other, say, big chunk of development, but also of ideas comes in, that is the VPU leveraging this long vector design. When we say long vector here with these boxes, I try to summarize it. So this is what you are used to in Intel. So 8 double precision element in one SIMD instruction. ARM SVE is defined to work up to 2048 bits. And here we are talking about this kind of size. So you can, in the same register, so one instruction is operating 256 double precision elements. Here you have the reference of the paper explaining the details about this. There is this important difference that you have to take into account, that while in an SSC, sorry, in a AVX or Intel machine, you operate all the elements in just one go, all the elements of your vector. In this kind of, so like in the RISC-V vector unit that we have, you take several cycles to process because the vector is huge. So you have just a limited amount of functional unit. So you have some latency. That's the latency actually that I was showing yesterday. So you take several cycles, and also depending which kind of instruction you're using, this latency can change. Good. So that's, I think, all the details you need to know about well, I'm assuming you are the scientist that comes with a million-line code with your weather forecasting application. So I think that if you have the feeling of this kind of architecture of what I said so far, you can start working. But the question is, how do I work with this kind of architecture? Okay. So here is the model that we promote, or the things that you can find in the SSH shell that was shared yesterday by Fabio. So you enter and you will find the compiler. And if you want your code to take advantage of this vector instruction, the first thing that we suggest is notice the happiness is going to very happy to more sad. Okay. So to stay happy, just use the compiler. Enable auto-vectorization and see what happens. So the compiler is smart enough to compile a lot of loops or a lot of situation in which you can already find vector instruction in it. If you already know, if you are well educated about your code, if you already know where the vectorization can happen, you can even annotate the code and so save some work to the compiler that is going to vectorize reading your input that probably is not so relevant. And then if you are getting a little bit more worried, you can start using intrinsics and built-ins, both for C, C++, and Fortran. And then if you really want to suffer, you can put your assembly as well. Here the message is there is a thin line here that is not drawn, but it needs to be taken into account. If you have your million-line code and you start doing this, your code becomes not portable. Okay, so if you have your library, probably you want to optimize and squeeze every linear algebra library. I mean, you can move here. If you have your code that needs to change from the EuroHPC installation of today and the one that is coming in 3 years, probably you don't want to go here because your code becomes not portable. Good. So we stay with this mindset of what we have to do in order to run our million-line code. The way we propose is you'll use it like a standard HPC system. Yesterday we did this tutorial in which probably we gave you a little bit the feeling. Compile your code, link your libraries. We have some vectorized libraries as well. Maybe it's not, the portfolio is not so rich like the CUDA libraries or the MKL, but we are growing. Write your job script with Slurm, as exactly like you do in other HPC system. Submit your jobs, wait for the result, and analyze the output. Now, analyzing the output, as you can imagine, may involve a tool that has been mentioned before. Okay. Anyhow, you will see it. So that's the way we do it. Now, if you have to listen just to one slide of my presentation, my suggestion is to wake up now and just listen this. Then you can go back to sleep, okay? Because here is basically the method we use with complex code. When I say complex code, I mean HPC codes that can run on multiple nodes that can be from fluid dynamics, weather forecasting, earth science, and as Jesus was mentioning before, even the LLMs of the AI hype that there is now. So here we start from here. So we have to prepare our applications. Okay, if you come with the weather forecasting application, probably we have to scale down a little bit the input because we don't have much memory in our prototypes, right? So then we have to start compiling with some compilers. Maybe you come and you want to use your own compiler because you have some dependencies and so on. Okay. We have to compile. We can provide our own compiler. You can use GCC. Start checking if you have dependencies, for example, to other architectures, like if you have intrinsics in your code, Intel intrinsics. So these kind of things are the things that we are doing in this step. Okay. So another important point that is done here is we study the structure of the application. Okay. So you look at one timeline and you try to see iterative patterns so that you know where the vectorization can happen. Then whenever this is ready, this is usually done on machines that are mini clusters of commercial available technology based on RISC-V. Okay. Then you jump on the auto vectorization part and emulation. Okay. So here is where basically we start doing, okay, we have to use our own compiler because we want to have control on which kind of binary is done. So the vector instruction are emitted. And we start emulating, meaning we don't need real hardware. We have emulators based on QEMU. And with that, we can have the feeling of how many vector instructions have been produced by the compiler, for example, or which kind of vector length we are able to use. Remember, we are using very large vector, right? So if we have a very large vector, 256 double precision element, and we just used 8 of them because the code has been tuned for Intel, maybe, we are wasting a lot of resources. So this is the kind of space in which we do this kind of emulation thing. Note that here we have a lot of development as well, because the QEMU emulators is done by the community, but we have a plugin that is able to inspect and collect information about the emulation itself of the application. And then whenever the hardware is available, we jump here. And here we have the execution on the EPAC back. Okay, so you can, as we showed yesterday with the gem, you can log in and just execute your code and see. Measure time, use the hardware counters. Maybe yes, maybe no. There are people in the room that are smiling. And start collecting real measurement about performance. So you can do the count of 1 over time that Jesus likes. So and then whenever you have this finish, so you don't just count instruction like here. You can really measure time. Then you merge these two, and maybe you find a version of the code that can be rewritten or kernels that can be. And so you jump around here and there, tuning your code. And then whenever you have 1, 2, 10 version of your code, you go back to the standard HPC installation, Mare Nostrum in our case, whichever machine you have, and see how if your code is still portable and how your changes affected the performance on the HPC machines that you have today, right? So what we don't want is harm the performance of the code after our, say, steps of optimization. The code should be equally portable and hopefully equally performant, okay? And so depending, yeah, still 15, okay, I can show you that this is the case in at least the 2 examples that I took today. Now, to go into the example, I need finished the important slide. So this the end of the disclaimer. So if you need to go back to your mails, done. I know there is one important thing here. I mentioned here the development of the QEMO plugin. Here there is also a lot of development. Because there are, as I mentioned, the support for the hardware counters, that is a little bit a jungle, and also the instrumentation things, right? We can look into the execution, but we can also look into the signals that are inside our chip, because the chip, we are lucky enough, we did it ourselves. I talk now as the EPI consortium. So we have visibility on the signals inside. For example, when I show you the OVI interface, so the signals that are passing there, we can spy them in the FPGA, like a logic analyzer. And so we can understand also performance from there. So there is not only the work on the application, but behind the scenes that are tools that are developed to enable this. Back to sleep. Okay, centers of excellence. Here, I need to introduce this because the examples that I'm going to show you are based on the center of excellence. I don't know if you are familiar with them or not. So these are the EuroHPC projects that are focusing on communities. Usually are communities of scientists that are gathered together to improve their scientific codes, usually for running more efficiently on a EuroHPC machine. At least this was one of the targets of the last call. So we are involved in 3 of them: plasma physics or plasma Pepsi, and we have, in each of them, we have just one small task. We are not really in the main stream, I would say, of the bulk of the development, because they have to prepare their code for exascale machines. But we are there and we can interact with them. So plasma physics, computational fluid dynamics, and geohazard, so basically geophysics. In all of this, we have RISC-V related activities, okay? That in all of them, we apply the same circle that I was showing here. So for us and now I will show you very briefly, I'm not going into details. These are really snapshots taken by the last face-to-face. So these are tables. Here you see the 4 steps of the circle that I showed you before. So first you run Scalar, then you emulate, then you run the FPGA, then you study the portability, okay? And on the lines of the tables, you have the names of the applications. If you're not familiar with them, no worries. I mean, neither us, we are familiar with that, at least with the physics that is behind. And what we do is try to have all these full of stacks, right? And we started 2.5 years ago, and we will continue 1 more here. And we try to gather information and insights. So this is the status of plasma Pepsi. This is the status of CEC, the fluid dynamics center of excellence, and this is the status of the earth science applications. As I said, I'm not going to details. Here is just to give you the feeling that that's not a toy. We are not executing AXP and switching off. We are executing a lot of real science that has a lot of complexity, okay? And the system works. So now the following question is, what do we learn from all of this? So for the last 13 minutes, if I can manage to finish by the half an hour, I want to show you 2 examples. One is, both of them are coming from the Fluid Dynamics Center of Excellence. One is ALIA. And here I have a little bit of, I have to introduce, because ALIA is pretty complex code. So if you run it on a parallel machine, you get an execution trace, something like this. Here you have time, here you have number of processes, and the colors are, say, phases of your application. That means that different physics are happening during, or different steps of the simulation are executing here. So here you have 1 step. Inside the step, you have different things that are happening. One kernel is called element assembly that has to do with the structure of the grid. So we took care of the blue part of this application. Okay, so our study focuses on the blue part. There is another important information that we use one parameter that is called block size. You can imagine like when you do blocking in a matrix multiplication. Okay, so you can do blocking at different size. No need to know more. And here are the values that we study. You can look at the numbers and see if you see there is no 30, but there are still something that probably is interesting. Okay, so we use a mini app that mimics the blue part. The mini app is divided in phases. We call it phases, but they are basically region of the codes in which you have one or more loops, because we are interested in loops for catching the vectors, okay? And we identified 8 phases. The sum of the phases is the mini app. And as I said before, we study and optimize only with the compiler auto-vectorization, no intrinsics. Good. So first step, you remember, we have just to prepare our application, prepare our input, and run on Scalar platform. And here is what you basically said. So here is our platform, was this small cluster of high five and match. And you change the block size, and here you have the total cycles. Basically, you have almost 0 effects of changing your block size. I mean, there is this sort of slight U shape, but basically. And so the only thing that you learn here is the percentage of total cycles spent in each of your phases. So you start learning, okay, phase 6 looks like bulky, okay? Because I'm spending a lot of time on that phase. Okay, good. So now I can try to enable auto-vectorization. So here I'm showing a plot that is a little bit of a spoiler, okay? I should not, so if I strictly speaking follow my circle, I should not have this now, okay? Because I'm still in the step in which I am, I'm not measuring cycles. But I do show you that if you take this and you enable the auto-vectorization, you start seeing that the block size has a big effect, okay? But also there is a step, there is one more comment that we have to say. If you take the code and you enable the auto-vectorization, the compilation doesn't explode. That's also a very good achievement usually, okay? Because we are working on something that is in continuous evolution, and we have codes that can be really a nightmare to compile. And this works basically out of the box. Good. So let's move to the step 2, emulation. Emulation, remember, I can look into the percentage of instructions that are executed in each phase. So here you have a table, different phases, and different block sizes. Sorry, I do some transposition between slides. It's not so, but you can follow, come on. So 8 phases, a block size, and you see the color code is basically giving you the percentage of vector instruction for each phase. Red is 0, and green is 30%. The 30 comes back, right? We know that experimentally, just we observe that if you have around 30% of your instruction are vectorized, then you are in the sweet spot. So phase 7 looks like okay, all green. We also see that if we increase the block size, it's getting greenish, darker greener, right? So it looks like that going to the block size high is helping the vectorization. And also what we see is that the bulky one, the phase 6, stays there. We don't know much about it. We also see that if we look at it in this way, in which brown is the memory instruction and white is the arithmetic, there is a lot of memory instructions that is also changing with the block size. That's, I mean, observations, right? We start collecting information. Then we jump to the step 3, and we can run on the EPAC VEC mapped into the FPGA. So the setup that we showed you yesterday. This is done in the old one, the RVV07, but it's not much important right now. Okay, so if we look in the bulky phase, that it was phase 6, we start looking at the some metrics, average vector length, for example, vector clock per cycle, CPI, and number of instructions. So these are things that you can correlate to the percentage there. So we see that we have a high vector clock per instruction if we increase the block size. That's looks usually is good. If you look into the average vector length, this is the important thing. If you increase the block size, you are using more and more your vector, okay? Until you reach 256, that is your vector size, and you stay there. That means that you are saturating all the resources of your vector unit. So every instruction, every vector instruction that enters your pipe is using all the resources that are there. That's the most efficient way of using your architecture. So in the third step, sometimes also we can address these three phases that they look 0% vector instruction. It's not nice, right? So by the way, sorry, in the meantime, I'm looking into percentage of time, not percentage of instruction, because I'm running on an FPGA. I can measure time. I can measure clock cycles. And so we started looking into phase 1, 2, and 8. So arbitrarily, not to stay here until tonight, I just show you what we did with phase 2. That is the red one here. So here, basically, you have same block size and percentage of cycle of each phase. And we start looking into it, and we spot that there is a problem that the compiler is not able to vectorize one very important loop. So we fixed this vector dim to block size. That is something that is completely okay with the algorithm. So this way, the compiler feels safe and say, okay, this loop now is vectorizable. And we compile, we measure the total cycles. So red is the original version, the one that was not vectorized. And then this pattern is the one that is vectorized. This is time. So you expected something that would go lower, but in reality, we are using more time. Why is that? So I'm enabling vectorization and I'm going slower. Here, the problem is the vector length. So we start looking into the vector instruction, and we notice that we are using a very tiny piece of our big vector. And why is that? Because the compiler is trying to vectorize this nested loop, in which the innermost loop, that is usually the one that has been vectorized by the compiler, is running over a limited amount of indexes. So basically, we are using just one small portion of our vector again. So we just swap these two loops, and now we go back and we measure the performance in terms of number of cycles, and we get the third column here. Good. Okay, so we increase our block sizes, and we see that we have this great gain. Remember, this is not the full application. It's just the phase 2. So I'm just working on a very small part. So here there is the the result with this version of vec2 plus the fixed of the vector length. So you see here is the percentage of the phase 2, that is the red with this pattern. When it's solid, it's because vectorization is there, so and it becomes stable and way smaller. Okay, so of course now I save the phase 1 and phase 8. I don't show you to you. This was just the idea of giving you the kind of things that we can do. And here is the result at the end. So we have the scalar version, the original vector. It means when you enable auto-vectorization, and then you have different attempt of getting the performance better and better. So block size on the x-axis, speed up compared to the scalar. And here you get basically the results. In this case, the best case is 7, almost 8x speed up of a fluid dynamic code that comes from real life, okay? With, I would say, very little effort and a big good point, that is the portability. Remember, the fourth step is going back to each PC machine and see if what we did works well also again in our HPC machine. And indeed, it's like this. Here you have the Intel cluster is the blue, And this is our RISC-V, and this is any CSX Aurora that is a similar architecture in which you have wide vector unit. Okay. So basically, if speed up is more than 1, it means that everywhere our new code is behaving better. Okay, I'm not going into details, but all these bars are above 1. Please remember, I'm starting from 1, not from 0. Okay, so that means that everything that we did on the code is helping our compiler and our vectorizer, but is helping all compilers and all architectures. So we effectively brought better code, okay? At least with the tools we have today. Okay, so that's very important. On top of all what we learned about our setup, we also make the people of the Center of Excellence happier, because now they have a slightly better code, okay? Now the second example, probably I have to go a little bit faster, but it's also okay to go faster, because this is the happiest case that you can have in this kind of work. They give you a code, you compile it scalar, you get say your baseline, you enable the auto-vectorizer, everything goes as you expect. So all the vector instruction are there, and all of them are using the maximum vector length. Done. 1 afternoon of work, and this application is done. And you get a speed up of 6 point something. And then you look into it, and there is some problem of huge pages, and then you enable huge pages, and you get 20x speed up. Done. Okay. Beer for everybody. That night is okay. But the day after, you ask yourself, can we do something else with this code? Is this... So you go back to the developer and you say, I'm talking about Walberla, by the way. It's a lattice Boltzmann developed in Erlangen. Okay? So you go back to the guys in Erlangen and you say, is this okay? And they say, yes, but this is the CPU code that is not really what we use. We use the GPU code. So you say, okay, then give me the GPU code. Okay, and then you look into the GPU code, and what they did for it's a little bit unformatted, but it's okay. What they did, this is the CPU code. You have a lot of loops with the function 1, 2, and 3. Okay, and this is the GPU code. They packed everything into a big loop. Okay, so that basically every iteration is a big kernel that goes to the GPU, take the GPU busy long time. Okay, so basically you have this space in which you can group loops, okay? And so if you go this direction, that is the GPU one, and you put it in our architecture, what the effect that you have is that you easily finish all the registers that you have for doing intermediate computation between one iteration and the following. So you do register spilling that goes to the memory, and this is bad. You don't want to do that because you are basically stressing your memory subsystem. You are losing time. But on the other side, if you stay here, your load and store, you're doing it anyhow. You are not doing it in the form of spilling, but anyhow, you are loading a lot of things, doing function 1, store it back, and then do it again, load, doing function 2, and store it back. Okay, so the question, so if you want the academic or the research question is, this is a sort of continuum space, not continuum, but defined by loops. So where is the sweet spot for my architecture? Okay, so yeah, I promise there was trace. So here there is a small quiz. Which one of the two have the group? These are basically the scalar instruction. These are the vector instruction of one execution. One of them has this setup, so all loops are fused, and one of them is the split. Do you want to bet or? Okay, so this is the group, and this one is the split. Okay, so you see we identified the 14 loops, 14 phases, and now I jump fast forward to the end. So we try to group them by colors. So here you have the 14 colors. We try to group them, all the greens, then the purples, the blue one, the purples, and the yellow. In the end, after 6 versions of this code, we end up gaining 10%. And one is saying, okay, yesterday you got 20x, and today you got 10%. I mean, I mean, maybe was not worth it, right? But here is the other angle that is answering why we are doing this. We are doing this because this is the structure of the code that they are using in the GPU systems. Okay, so this is really what makes us understanding which is the current state of the art of their HPC code, and porting that into our architecture without CUDA, without all these kind of things. So there is not only the going back to the developer and say, oh, this is 20 times faster, that's it. It's really understanding our own setup with our own tools, what we can. Anyhow, 10% is always a nice thing. Conclusions. EPI decided to explore an extreme design point. This huge vector length is not so common, and the codes are not prepared for that, not all of them. Studying complex scientific code. Did I do something? Okay, it stays. Study in codes, complex code is very important to validate the system software, to provide feedback to the RTL people, because there is one other angle that I didn't touch, but basically we used a lot of this microkernel to catch bugs in the RTL design as well, and to develop portable vector-friendly codes, as I show you to you. And then the evidence so far are that these studies are worth it, are very important. We can improve the compiler, we can improve the applications, we can engage with the scientific community. We showed you yesterday, you can ask access and run your own code. It can be used for debug next generation machines. And it is a scalable environment, right? What we showed you yesterday, we had the one setup with the old SDV, one with the new one, but if tomorrow we have a new chip, we can include it. And all the tools can be adapted easily, more or less, for having the same kind of studies. Okay, so it's not something that is done for EPI and stays in the EPI box. It should be used. And that's it. I think that's... Here I will share there are references with papers and study that we did. The one of Alia has already been published, so if you want to dig the details, you can do it. And here is where you can take the pictures so they can pay me the travel for today. And best regards to Matteo. No, it's the acknowledgement of our project. I'm between you and your coffee, so if you have questions, otherwise we can go and have coffee. Thank you.
Questions for our speaker? Questions from this side, yeah.
Thank you for this great presentation. I'm going back to the result on the Intel and Aurora clusters after optimizing for VEC. So we could say that actually the methodology for vectorizing is not tied to one instruction set. I mean, when you vectorize for one CPU, you vectorize for all of them. Is that right, or are there some cases where this will not happen? Or
I mean, coming from mathematics, the words have a lot of importance. So when you say when I vectorize, is not me, is the compiler that is vectorizing. What I'm doing is I'm helping the compiler. So the help that I'm doing, writing a Fortran, say a Fortran code written in this way, the way in which we wrote it, I'm helping the compiler. And it happened that I'm helping not only my compiler, the API ones, but I'm helping all the compilers. But yes, the short answer is yes. Whenever you do these kind of changes, you get better code for all the compilers, independently on the instruction set architecture.
thank you.
Thank you.
Other questions?
Thank you for the very good presentation. Just, I think it's very simplistic, so maybe I'm not thinking something. So you have those big vectors that run in small chunks.
Yes.
so they produce some latency. What will be the difference if you just use a small vector unit that runs many of those small vector commands?
Well, one big difference that we see is in the I wanted to find the picture with the one big difference is you have a lot less instruction flying around. The handling of the loop is lighter because sometimes I mean you divided the loop by 256 basically. So compared to the Scala, right? This is one thing. The other thing is that you create workloads for your CPU. Now look at the work that the CPU is doing like a Tetris game, right? Scalar instruction are small pieces and vector instruction are big pieces, where the size is basically the latency that. So if you play well your pieces, you can squeeze less empty spaces between your, right? You can overlap things, even if you can overlap arithmetic and memory instruction that are vector instructions, right? So if I have a vector instruction, I have to go to the memory to take a lot of data. So it can take a lot of time. If in the meantime, I have two vector register in my vector registers file ready for computing something else that is not dependent on the, well, I can do these two things at the same time. So it's not only a matter of having 8, I mean, this approach of saying I have 8 functional unit is equivalent to AVX 512, period. No, there is a lot more of implications in the dynamic of the execution of your binary. And maybe I'm forgetting others.
I'm covered. Thank you very much.
Questions from the remote attendees?
No, thank you.
Okay. Any other
Thank you.
question from the room? Well, if not, let's thank our speaker again.
Thank you.